Let's try a weak acid base titration calculation. These are going to be a bit more complicated than your strong acid, strong base, but they shouldn't be too bad. Our lesson objectives. We will calculate the pH of the titration at the start, before the equivalence point, at the half equivalence point or midpoint, and at the equivalence point, and then after the equivalence point for a weak, strong titration. Calculate the pH of the following volumes of 0.1 molar HCl to 25 milliliters of 0.1 molar ammonia with a Ka of 5.6 times 10 to the negative 10th. Now, when we look at a problem like this, we note that we're working with a weak base, and so we're going to have to do ice tables, and we're going to have to use Henderson-Hasselbalch. So, additionally, and we will show why this is the case as we do the calculations, we need to know both the acid ionization and the base ionization equations to make this work. So we know that the conjugate is going to have a back reaction, so we need to account for it in our math. The equilibrium we establish will depend on the titration being before or after the equivalence point, or at the equivalence point for that matter. So before we do anything else, we're going to write the ionization equations. We'll determine the equivalence point and the midpoint. Now you may be wondering, why do I want the midpoint as well? We know that according to the Henderson-Hasselbalch equation, when the anion equals the acid, we'll have a pH equal to pKa, because the log of anion over acid in that equation will be equal to 1, or sorry, will be equal to 0, because anion over acid is 1. The math is super easy for that particular data point, which is why we go ahead and do it, because we're like, yay, easy. I like easy. All right, so let's try to figure those things out. We've got our base ionization, we've got our acid ionization, and I calculated Kb based on the Ka by using the Kw. I'm not going to show that because at this point that should be old hat. So I go ahead and I calculate the midpoint. So I take my molarity times my volume in liters, and I get 2.5 moles of NH3, and then I divide that by the molarity of my HCl, and I get that the equivalence point should be 25 milliliters. The midpoint is half of that, 12.5. So let's go ahead and try some calculations. We know that our midpoint was 12.5 milliliters, which means at that point the pH equals the pKa, so we take the negative log of the Ka and we get 9.25. Super easy. We already did the midpoint. We know the pH there. Yay! So before we start our titration at volume of 0, we know that the base ionization equation will apply. That's what's going to happen. So I calculate Kb from Ka using Kw. I already did on the previous slide. My Ka is 5.6 times 10 to the negative 10th. And we're going to go ahead and set up an ice table. So we're going to have the 0.1 molar NH3 in equilibrium with NH4 plus and OH minus, which means that we're subtracting from ammonia and we're adding to the other side. Now, I'm going to go ahead and plug that into the Kb equation. Okay, and when I solve for x, I get 1.3 times 10 to the negative 10th molar. And I highlighted OH minus because that is important. When we use the base ionization, we get the hydroxide concentration, which will not give us the pH. So we do 14 minus the negative log of the hydroxide concentration in order to find pH. And at our starting point, the pH for this particular solution will be 11.13. Not too bad, but really, pay attention to what species you solved for, otherwise you will definitely get the wrong answer. With relatively little effort, we have now filled in 2 of our pHs. Let's go ahead and do a third before the equivalence point, the 7.5 milliliters. So we decided we're going to work at 7.5 milliliters and figure this thing out. For a weak acids, strong base, or a strong acid, weak base, we can use the Henderson-Hasselbalch equation to solve for pH, because in the act of titrating, we make a buffer solution. We have our acid and our conjugate base, or we have our base and our conjugate acid. They will be formed. So why am I bringing this up? We can use the Henderson-Hasselbalch equation in order to find our pH. Well, the Henderson-Hasselbalch can be worked with in both moles and molarity. So we can do our math with just moles, and we don't need to convert from molarity and moles back to molarity again in order to solve the problem, which makes your life so much easier. Now, the second point I'm going to make is that we can actually work in millimoles instead of moles. And you may be thinking, wait, what? Why would that be convenient? First off, let's take a look at this equation. So if you multiply milliliters times molarity, you'll get millimoles because of this following series of conversions. So if we went from milliliters to liters and then multiplied that by molarity and then changed that into millimoles, you'll notice how this factor of 1,000 cancels that factor of 1,000. Convenient, isn't it? So if you just take milliliters times molarity, you get millimoles. That was stupid easy. Okay, now we are doing an acid-base titration. The acid-base reaction is going to happen. It is energetically favorable. So we're going to calculate what changes the amount of material using a BCA table, and then we're going to solve things. And I know that I'm starting with 2.5 millimoles of NH3. So I go ahead and I put that into my ice table using the base ionization equation, and I find the concentration of my ammonia and my conjugate acid, right, the NH4 plus. And then I put it into the Henderson-Hasselbalch equation. So pH equals pKa plus log of anion, which is the NH3, over our acid, or ammonia, which I know doesn't look exactly like what we're used to, but it's still the same idea. And that is equal to 9.62 at 7.5 milliliters, which honestly, you were thinking it was going to involve quadratic equations and all that, and it doesn't. In the end, we're fine. We're done. It's not that bad. Now, I will tell you, at the very beginning of the titration, the Henderson-Hasselbalch will not work. Why won't it work? Because we haven't created a buffer yet, right? We have to have at least 10% of the stuff acting as a conjugate. So if you take 0.1 times your equivalence point volume, in this case you would get 2.5 milliliters, anything 2.5 milliliters or less will not be buffering. It won't work like this. You actually have to do the BCA and then the ice table and then the solution for the quadratic equation in order to get that answer. But we're not going to do that. We're not in that regime. Okay, so we filled in 3 out of our 5 possible data points. We're going to do the equivalence point next. We remember that that was at 25 milliliters. Your first instinct might be to start with the base ionization equation, because that's what we've been doing. And then fill in the ice table. And I left it with millimoles just because I didn't feel like changing to molarity to make this point. Take a look at what we have here. We end up with negative X for hydroxide. You can't have negative moles. That can't be a thing. So this makes no sense. Don't do it. At the equivalence point, we have to switch from the base ionization to the acid ionization instead. If you were doing a weak acid, strong base, you would switch from doing acid ionization to base ionization instead. So you're always going to have a switcheroo of the equations when you get to the equivalence point. All right, so we've switched to acid ionization. We're not in the buffering region of the titration. We will not be in that region from now on until the end of the titration. So therefore, we have to calculate molarity and use an ice table. So our total volume at the equivalence point is 25 plus 25, which equals 50 milliliters. And we know that we had 2.5 millimoles of ammonium. We got it in the ice table from before. because we started with 2.5 millimoles of ammonia. And for the same reason that we could just do molarity times volume in milliliters, we can also do millimoles divided by volume in milliliters and still get molarity. So we take our 2.5 millimoles, we divide by 50 milliliters, and we get molarity. And we go ahead and fill in our ice table. So we have 0.0500 molar, and we're pushing toward the product side. So we plug all that in, and then we put it into our Ka equation. And we ignore the minus x because 5.6 times 10 to the negative 10th is super tiny. So we know that that's not going to matter. This is how we end up with a pH at the equivalence point less than 7, because we are doing this backwards equilibrium. So we solve for x, sorry, and we take the negative log of that because we are solving for the hydronium ion concentration, and we get 5.28, which, you know, all in all, that wasn't terrible. It wasn't terrible at all. But it did require thinking things through and doing a number of steps. So whenever you're doing these types of titrations, make sure at the very beginning you calculate the equivalence point, and then you know which regime you're in mathematically for which region. All right, so we still have to do after the equivalence point. All right, so at this point we've filled in, 4 out of 5 of our points, and we're going to go ahead and do after the equivalence point, which we know is going to be acid ionization. So we start with the fact that we've got 30 milliliters, and when we multiply 30 milliliters times 0.1 molar, we get 3 millimolar H+. We're going to subtract off the millimoles from ammonia, which is 2.5, and we get 0.5 millimoles of H+, and 2.5 of ammonium. Our total volume was 55 milliliters at this point, because we do 30 plus 25. And so we can calculate the molarity based off of that. At this point, we've done our BCA, and I didn't represent the entire table. I just did the shortcut calculations, but hopefully you understand what's going on there. If you don't, please go ahead and do it for yourself. We're going to fill in our ice table. Okay, so we're starting with 4.5 times 10 to the negative second molar ammonium, and we're going to have 9.13 times 10 to the negative third molar H3O plus at the very beginning. If I were to put this into the Ka equation, my Ka is 10 to the negative 10th. That plus x for the hydronium, not going to matter. It's not significant. So I can just straight up take the negative log of 9.1 times 10 to the negative third, and I get 2.04 at 30 milliliters. So after the equivalence point, all you need to worry about is how much H plus is in excess. You take the negative log of that, you're done. All right, to summarize, write both your acid ionization and your base ionization equation for the weak component. The weak acid will start with acid ionization before the equivalence point, and you'll use base ionization from the equivalence point onward. You can use the Henderson-Hasselbalch equation once the buffer has formed. For your weak base, start with the base ionization before the equivalence point, use the acid ionization for the equivalence point onward, and again, use the Henderson-Hasselbalch once the buffer has formed. Use your BCA tables to determine the starting values for each species. Use the ice table for the initial pH, but otherwise the BCA tables and a conversion to molarity as needed. And finally, pay attention to if you are solving for OH minus or H plus in your BCA or ice tables when you go to calculate pH, because nothing hurts worse than realizing you're off by a bit because you just forgot that last tiny step and you did all of those other steps correctly. Okay, hopefully this will all run smoothly when you try to do the problems in class.